Greetings everyone, Engineer Leonardo here. On this video I'm gonna do a different approach from my other videos. You see that I usually record a video using the computer in a PowerPoint presentation or Word file. So in this video I want to try another approach using my board. You can tell in the comments whether you prefer to me taking a class using a board or a PowerPoint presentation or Word or writing equations in a Word file, for example. Okay, so in this video I'm gonna do a derivation of the Bernoulli equation in its most classic form, neglecting effects of gravity and for a steady case. Okay, so let's begin. So first of all, we start as always as the full Navier-Stokes equation for incompressible fluid flow, and we're gonna neglect the viscous forces here. So what we are left is known as the Euler equation. So we'll write it down here. So in case you don't recall what this equation means, is specifically, generically speaking, in a simplistic way, the Newton's second law applied to a differential volume of fluid. So here we have the mass times acceleration term, and here we have the sum of forces. So we neglect the viscous forces, and now we are left only with the pressure forces. Here we have our temporal time acceleration and our convective acceleration term. And here, of course, is our velocity, and here pressure and density, right? So now I'm going to open up this equation, which is in its vector form, in its two Cartesian components in 2D space. Okay, so in the x direction, and the y direction. Okay, so for simplification purpose and for simplicity, for make it more straightforward, I will not consider the gravity effect, but you can make a similar derivation including the force of due to gravity. Okay, so we're gonna do another simplification. Remember our velocity vector here is denoted by this. So v is equal to u and v. Okay, so this u is the component of velocity in the x direction, and v is the component of velocity in the y direction. So you can derive an unsteady Bernoulli equation, but for now we're gonna just assume that our flow is steady, so this term here vanishes. And what we are left, I'm gonna divide these two equations here for density, so we are left with Okay, so we consider steady flow, and here we have x, y direction. So, well, so far so good. What we have up to now is these two equations here. It's the steady order equations in 2 dimensions. Of course, for in viscid flow, considering all effects of viscosity. So what we're going to do is integrate this equation along the streamline. A streamline in a fluid flow has its velocity component tangential to its line. Okay, so here is an example of the streamline. If you're going to look at a real-life example of what streamlines looks like, consider, for example, pipe flow, where we have reduction of its cross-section, right? So flow is coming, the flow rate comes from here, and then we have a reduction of its cross-section, okay? So the streamlines of this flow is going to look something like this. Here we have streamline, and then another streamline. Of course, if it is a turbulent flow, this will be the streamlines of the mean flow, the average flow. And if it is a laminar or viscid flow, it will also look like this. Okay? So these are the streamlines for this flow in case you are not familiarized with streamlines. So back to the problem here. We're going to integrate these equations along a certain streamline. So here we have our streamline in red and the velocity component of the flow in a certain point. We have this differential of the streamline, which has this relation here, the relation for the rectangle. So it has an infinitesimal form of this streamline element. We have its projection in the, here it's flipped. I swapped the x and y. Here it's x and here it's y. Okay. So here it is dy and dx. Okay. So what we're going to do is establish a triangle relationship between this differential here and the velocity components. So using the triangle relations, we have that dy has a relationship, is proportional to v, right? Divided by dx and here by u. Okay, so what we have is u dy equals v dx. Okay, so this relationship here comes from here. Okay, these two triangles here, right? Here we have our infinitesimal rectangular triangle, and here we have our velocity triangle, these two triangles here. So far we obtained the two components of the order equations for steady flow and viscid flow in the x-y direction using Cartesian coordinates. And we obtained this relationship here for a streamline of the flow. And now we're going to use an identity from calculus, specifically two variable functions, which is the following. We have the differential of a certain function f, which is a function of x and y, okay? So this differential here would be equal to df dx, partial derivative, dx plus df dy dy, okay? So we're gonna need this more this relation here to derivate the remaining of the other equation. So we multiply this first equation by dx and we obtain the following. Here we have and we multiply the second equation by dy. So right? So we can rearrange these two equations here. I'm gonna continue up here, so erase. So I'm going to rearrange these two equations here a little bit. So we have u dx plus dx equals and so remember that we derivate the relationship for the triangle, which states the following: that u dy equals v dx. Okay. So this we can substitute for this, and this we can substitute for this. Okay. So using this. Here and here, we obtain that the following: u plus u right? So far, so good. Also remember that for a two-variable function, remember that u is a function of x and y, and v is also a function of x and y, okay? So consider f a generic function, which is function of x and y. We have that this differential here is ef ex, the two partial derivatives here. So we can use this identity, this relation here. So we can put u in multiplying this whole equation. So we obtain u x and v dv dx plus dv y dy equals okay, we are almost there. Here we use this identity here and here and here. So for x and y direction, this is equal to du and here dy. So let me erase right here. So we're writing these two equations. Here we obtain, it's a little bit of reflex over there, u equals and v dv so we can sum up these two equations here and we obtain u plus dv plus, I put this to the left side, I put the pressure term to, I moved it for the left hand side of the equation. So equals 0. So as you may already notice, this is already equal to Tp. Okay, so rewriting this again, u du dv plus Tp divided by whole equals 0. So we need to integrate this equation along 2 points of a streamline. Okay, so let me erase over here. So consider the streamline that we were working previously. So here is our streamline S, and here's velocity component. And here, let's say it's point number 1, and here is point number 2. What we're going to do is integrate this equation between point number 1 and point number 2. So here at point number 1, we have U1, V1, and pressure 1. We have the velocity at point 1 and the pressure at point 1. And here we have U2, V2, and U2. Right? So integrating this equation here, we obtain the following. So U du 1, 2 plus 1, 2 b plus equals 0. So this leads to, here we have 1 and 2. U squared divided by 2 plus, this is the point, okay? It's not the number, it's the point. So I'm going to circle it down for avoid misunderstandings. So B squared plus pressure. Of course, this is density, a constant density, so we don't have to consider here in this derivation. So this leads to 1/2 U2 squared minus squared plus U2 squared minus So we already obtained the Bernoulli equations, but we must rearrange this equation here. So I'm gonna put this equation in terms of the absolute value of the velocity, or modulus of the velocity. So we have the magnitude of the velocity at a certain point. Let's say at point P equals UP squared here plus VP squared, or we have squared so we can rewrite this equation here in terms of the velocity magnitude. So what we obtain is that V2 squared is U2 squared plus so this is not the same V as this one. This is the V for velocity magnitude, the capital V. Okay. So this said, and we obtain that I open this term here, okay? So rearranging the terms, we finally arrive at the famous Bernoulli equation. Here, E2 squared divided by 2 plus E2 okay. So if we included the gravity term, what we will obtain is the following. It will look like this. So H2 is the height of point 2 in the z direction. In this particular case, we are considering that the velocity is acting on the y or z direction. And H1 is the height of the first point. So this is the Bernoulli equation neglecting effects of gravity, and here is Bernoulli equation for effects of gravity. There are plenty of other versions of Bernoulli equation, including if we have hydraulic machinery providing energy for the flow, or if we have a turbine or losses. Okay, we can account this equation here for head losses in a pipe flow, for example. Okay, so we have derived the Bernoulli equation. This one is a good exercise for those who are taking fluid mechanics classes. We derive this equation using a similar logic, similar manner as I did for this equation here. And also there is an unsteady Bernoulli equation, which I tend to cover in another lecture. Okay. Hope you enjoyed. Don't forget to subscribe, to like, to comment, and to share this lecture with your friends, okay, and classmates. Thank you. Hello. So in today's video, we done a derivation of the famous Bernoulli equation. So we made I'd like to talk about a little bit about its limitations, since Bernoulli equation is one of the most misused equation in fluid dynamics. So first of all, we start from the Navier-Stokes in incompressible form. So one of the assumptions is that the flow is incompressible. Okay, so the equation we derive is not valid for compressed flow. Second, we made assumption that viscous flow are negligible. So we neglected the viscous term, the viscous forces, which lead to the Euler equations. Okay, so Euler equations are the Navier-Stokes equations without the effect of viscosity. So another assumption we made is that the flow is steady, so this equation is not valid for unsteady flow. Although they are a form of the Euler equation, the Bernoulli equation, which is valid for unsteady flow. Second, we integrated this equation along the set of equations obtained from the Euler equations along the streamline. So in order to use the Bernoulli equation, you have to apply it along 2 points which are on the same streamline. You cannot change between streamlines. If you change between streamlines, you are doing incorrectly. You are violating the derivation of the equation and the assumptions which are implicit in the equation. Okay, so this equation is valid for incompressive flow, viscid, and steady, and along a same streamline. Okay, you see that for example, in hydraulics, this equation is applied for turbulent flow. Okay, so in turbulent flow, it's a good approximation to consider it viscid, and we have what we call as a mean flow or average flow. So we treat these streamlines of the turbulent flow, which of course we know they don't stay the same, and they vary with time. They are unsteady in a certain way. Steady flow in a turbulent steady flow in a pipe. We apply the Bernoulli equation for the mean flow. So we are dealing with mean velocities and mean pressures. And with little correction and with a very negligible error, we can apply these equations to turbulent flow. But be careful, because these are very specific, and we cannot do this for every turbulent flow with mean flow. Okay, not every mean flow generates what we say streamlines, which resembles the characteristics of a laminar in viscid flow. Okay, so see you next video. Bye.